So coming back to the 7-layer ISO-OSI example page for corporation. And here I just gave you a certain number of examples for the 7th layer, so the application layer, where we think about multiple description coding, cooperative web browsing, file download, localization, and then going down to the medium access control and even to the physical layer and the RF baseband parts. So for all of that, I brought you 1 or 2 examples just to show what has been done so far and where the gains are, right? Good. First, I think because it's easy, because it's very easy to grasp an idea of something that we called CoBlock, something that got the Nokia Innovation Award in 2008. It's about cooperative location. Back then, you had the way to locate things with GPS. GPS was not, you could not have it inside. It was even draining the battery a lot and not very precise, right? And here the idea was quite simple. What if I could make my location based on the cell ID? I think triangulation is well known. So if the network operator wants to do it, he will use several cell towers, take the signal strengths, and then calculate where you are. If you want to do this on your mobile phone, it's not so easy because if you have a programming API, you can only see one, so the current base station that you're connected to ask for the signal strengths and so on. It's not totally true. There was some phones like the Nokia S60, one of the first ones where you could really have a memory dump, and when you have the memory dump, you could read out the cell IDs and also the signal strengths to those devices. As this was not possible for all of the devices, we thought, what can we do if we only have the signal strengths to one of the devices? In order to do that, we made some measurements, and we had students going around the city of Aalborg, all the streets, and what they had were a board with phones on it. And every phone had a certain network operator. This was TDC, for example, one of the network operators. And when you went down, you see, okay, if I'm here, I'm very close to this cell tower. We wrote down our GPS coordinates and also the cell ID. That we did also with Telia, right? And we did it with others. And then if you put all of them together, it looks like this. You have a map of different network operators. So if you are then standing in one position, and if you would get all of the 3 IDs, you could really precisely derive your location. If you only have one, your own, then you might say, I'm in this region, right? And you cannot get the cell ID of other cell towers of your own network, and you cannot even get them from the different network because you don't even have a SIM card for that. But now you ask via Bluetooth other users to share their cell ID with you, right? So if they're in Bluetooth range, it's not so far away, and you just say, tell me your cell ID, and the database is well aware of me. So if I have 2, I can already narrow it down. If I find a third one giving me information, even a little bit more, right? So if you look at this, you could say, if I have no cooperation, I could use the cell ID. Sometimes also sectorized antennas could help you a little bit, make it more precise. But if you have cooperation and you overlay all of these cells, then you see the inner circle here. And this might be your area where you are. So this are the measurement points, right? So on the board there were 3 phones on 3 different operators, and we measured all of them. Now if you want to do it, here you see again the different TDC, Telia, CBS as you had before, overlaying them quite nice with the area where they have been supporting the certain areas. And then you see here what we have done. On A is the GPS location. On B is the derived location. So this green circle tells you the area where we think we are if we are alone, just with our cell ID. And this is if we get a second or a third cell ID here. So if you look at the area, you can see that we shrink down the amount of shrink down the area where we might be in with 3 mobiles by a factor of 6, right, which is quite good already. As I said, this was quite an interesting project, and some of the Nokia people followed up on this, while we had another project then, not looking into collaboration, but into sharing content. And this was together with NBC. So in New York, they had an idea how to offload their servers. So they were well aware that there was piracy going on with their material, their content. And what they wanted to do is to allow people to share the medium, but they would be happy to have access to the way how they made advertisement to it. So what they want to have is, if you have a premium user, so they have a premium account and you have to pay for it, then you would you could just download the content. If other people are there, they are not willing to pay for the content, but they need somehow to be convinced. What you do is you allow them to get the content from the paying users. And this is how it would be like that some people are there that have the content, and he will now broadcast the content that he paid for to others. And if a fifth one wants to join, first of all, he has to play an ad, right? And after the ad with some Budweiser beer here, I hope that I'm allowed to show this here, but I think it's okay. So after the ad, the content will be played, right, for a certain time, and then they will play an ad again and again and again. The advantage for NBC here is that they will not come to their servers, right? And this costs them energy, and this costs money. So what they want is let the users distribute it, as long as we are able to integrate our advertisement for that. Good, this was a very easy one on application level. Another one, very shortly, was to show cooperation among users to free some communication. And here you see something what is called SMS cooperation. And the idea was, can I send a message for free between 2 mobile phones? And this is possible if you use your collaborative cluster around you. The idea was based on something that was well known in Italy as something called Trillo, where people just called you, but you should not take the phone call because they will hang up, and that tells you, I think of you, or whatever. That was the time when you still paid for every phone call. Now you even paid for small messages at the time, and what we could do is just to say, why don't we do the following? We take one device that wants to send a text message for free to the other device. So imagine this one here is in Dresden, and the other one is, for example, in New York. So this guy will find with Bluetooth some devices around him and will say, listen, I need your help. Please send me all your mobile phone number. So he will get the mobile phone number, and somehow the other side will do the same, right? So they agree now on something where they know each other's phone numbers from these devices as well as a database. And what we will do now is just to use the way we are calling each other to convey a certain message. For example, if you have the bit sequence 00, so if you read from here 0010, this means the first of the first group, that is the master himself, should call the second of the second group. So there will be one call going like this, be placed here. After the call comes there, you hang automatically up, and then via Bluetooth you send the master here the message that the first slave has been called by the master of the other group. And this master can then derive, this would be 0001, reading from the right to the left. And then the second call would be 11. This is the fourth guy down here calling the 1 0 1 0 from this side, so the second one of the slaves in the second group, and there this call will be received. You just hang up automatically and you do that. And we have implemented such a scheme, and I think it took us something around 3 to 6 minutes to convey a full SMS at the time. We even came up with a way of compressing the data, so it was 1.5 minutes in the end to convey data from one corporate cluster to the other one. That is an interesting fact, because with that we demonstrated something that we call a post-Shannon theorem, and this is something that we will discuss in ComNet 3 lecture. So if you want to know about something like this, you have to listen into ComNet 3, post-Shannon. Good. If you want to share video services again, the NBC video example was one of them, but we can even make it more interesting and more quantitative from the energy perspective. Think about the following, right? You have one base station or one server that is giving out the service to one user, right? Due to his capabilities, he will only get a very bad video quality. Now, the lady down here, she gets 3 streams, and these 3 streams, higher data rate, will give her a better picture. So this is realized, what we call it, multiple description video. Multiple description video is not like a layered video where you need a base layer and then the enhanced layers on top of them. Here, every stream is the same, and the more streams you get, the better it becomes. So if you get 3 streams, the quality is quite good. If you have such a solution with multiple description coding, you could even give multiple description coded video to each of the users. They will exchange it down here, and then they will get the same quality as the lady that you have seen here. So that was quite interesting. And what we did is we implemented that. Well, it was a project 2003 called Edwin. You know even why it's called Edwin. We had a server that could stream different streams to the clients. The clients could cooperate. And we had Wi-Fi technology. It was 11B and 11A. And I think we used 11B for sending out the descriptors and 11A for cooperation. In order to make it work, there was no multiple description video codec at the time, so we built our own. And this server really created the 4 different streams and sent it out. Interesting was for us to investigate what would happen if now one client would go out of the group and come back. He would always get his own descriptor, but he would not be able to collaborate with the others. And the goal, and it was also achieved, was that the video was be fluent, but the quality will degrade dramatically for this guy. And if he goes away, that also degrade a little bit for these guys because they are missing the 4th stream. Now, if he will join again, then the descriptor will be added here to the clients, and cooperation will go on, and all 4 would have the high class service in the end. So unfortunately, we never made a video of that. It was a quite cool demo. I just show you some of the user interfaces, what you could see on the controller. Here you see an interface. This was called Edwin with a bitrate of 54 megabit per second, where you receive something, and here you have another one at 5.5 gigahertz. And here the bitrate is not there. This was for the short range, for example, at the moment not active. And here you could see the virtual data plot. Here you see the data rate that comes in only over the first internet interface. Then there's a second stream coming in and a third stream coming in. And this is how the data rate goes up. Here you see the display with you're getting a stream from the server and you're cooperating with 2 other devices, but not with the second one here. And here you can say cooperation on and off and start the playing, stop the playing as you want. Good. And this was then the outcome, more or less. It looked like this, with no cooperation, with cooperation, etc. Good. Then if you want to look a little bit more into detail how this could be done, if you, for example, are not using here like we did the IEEE.11, but if you would look use DVB-H. DVB-H was a technology. DVB-T is maybe known as television terrestrial. This was for the handheld. So what you could do is you can, from the base station, just submit 3 streams, and you just would say, I would like to get all the 3 streams, even though I'm only interested in one of them, and I will take 2 of the streams and send it to my colleagues, and the colleagues will do the same for me. The interesting part is that on DVB-H you save energy by having high data rate bursts and then switch off the radio. And by cooperating, you can switch off the radio for longer times and saving a lot of energy. Question is how much energy you would then invest by the short-range technology. And here is an example of 2 already cooperating devices, and the green one here is moving over a time axis. And what will happen then? So in the beginning, you see the 2 devices, they are cooperating and they have some energy gains. And the green one, because it's out there and it's not able to cooperate, will not have any gain. Once it will come into the range of the red station over here, what will happen is the red can cooperate with the green and the blue. So the red will get a lot of gains, while the green and the blue will get a little bit less. So here you see the blue one is not very happy that they all agreed to cooperate. From the system perspective, that's quite good, but not from the individual perspective from the blue one. The green is happy and the red is happy. The blue one, not so much. If then the green one comes into the area where the red and the blue can also collaborate, then they all get the same nice gain. And then if the green one is leaving again, now the red one is punished and the blue one stays high, and in the end the green one is out of the cooperation range, and you see what happens here. This is if the equal exchange packets. You can even improve it a little bit by making this unfairness a little bit better. Then you need a balanced energy consumption. I don't will go into the detail, but you see the advantage here. What we do is the green one comes up, and here, even though the red one would be the one that gains more, here it will gain only, you would lose a little bit compared to before, compared a lot to the other time there, but you see that all 3 must be happy here. And then they get all the gain back then, and back here there's a little bit of degradation for the blue one. But to convince all 3 stations that cooperation is the good thing, maybe they like this more than this one. Without doubt, both have a gain, but sometimes, if ethics comes into the picture, here the blue one could say, I don't cooperate with the green one at all. And you don't want that. So something like this is beneficial. Here are some values. We might need this for the exercises. What kind of values we assume for this cellular link, for the short range, for the different ones. I think then you can calculate later the energy by yourself once we have explained to you how to do that. So we had another one, cooperative web browsing, because the examples before, they assumed that we all want the same service. But what if people want the different service? So what if there are 2 users with browsing 2 different web contents? Can we still have a gain there? So interesting is also that web browsing is not a continuous service, right? So it might be that I will download something and then you download something. So there must be some payoff, and the payoff is delayed. You remember the monkeys that had this payoff tolerance? Something like this we need. And we will show you that there's a benefit in the downloading time, and that the energy-wise, the short-range link is an extra cost here. Imagine the following. You have some content that you would like to achieve. Now the left or the right. You would get it over both cellular links, and the one or the other one, they are sending it to each other to help each other. So I will download content for another person. I'm not interested in that content, but I'm just doing it to help. So where's the benefit? So first of all, if you look at web browsing, every web page is based on an object. It's not one clumsy data block. It's about the, once you go to the web page, you get a header information, and that tells you about objects, how large the objects are, and for each object, you're opening up one TCP connection. Then your job is to order these objects in size, to give both devices maybe the same task, and say, please use these objects and share them later on. So what we could do in a cooperative web browsing is, first I have a page request. I go to the web server, I download it, and then I will read a page. Then I will ask a new page. Then I will download it and read it again, and so on. This is a web browsing session, right? So if we have two devices, and what we could do is, if we stand alone, you say, I'm going to get the header information. I'm downloading everything myself, and I'm reading it. And the second one will also do the same and say, I'm downloading a web page, and then I read this. So if you do now a cooperation, you see that while the first one downloaded something, the second one did not do anything. So you could ask him and say, can you help me? So we both download my contents. You send it over the short range to me, and you see now the download phase has been reduced. And the gain is just the time you wait for it. And then once you have done that, so the second helped the first one, now the first one can help the second one a little bit later. So here you only need payoff tolerance, right? You just, the second one have to have the idea, yes, he will help me later on. How can you achieve this? It's quite easy. As this, we think this will happen over and over again. Maybe in the first you invest something like a certain amount of bits that you will help to contribute. Maybe you say, I will take an object, the smallest, and help you to show that I'm cooperative. And then if the other one helps me, he already takes 2 objects, and then I take 4, 8, and so on until we create some trust in the cooperation. So the way how you build up trust is very critical here. Because if it takes too long, then you cannot take the full advantage of the cooperative cluster. But if you take it too quick, you can be victim of being fraud. Another thing is, what happens if we have two phases where the phases are going into each other. So now, if you have a longer phase of downloading something, and you see that now they are more or less in parallel. What would happen is the first device would start, then download in a collaborative way. Once the second will start, they will split each other. Everyone will do its own job, and later on, once the initial device has been done and the user starts to read, it will go back and help the second device to download the content. And if you do that, there's a little bit of calculation you can do. So if you have a certain number of devices and you have an average download time, then you could think, what is now the best that I can achieve? And when I go back, normally we say that the reading time is 4 times as much as the download phase. These are some numbers we get from the literature. If this is true, then you will see that the blue line would say, okay, everybody around me, please help me. So the more devices you get, the better it is. But if you know that you also need to help others, then you would say, yeah, there's only this download time of 2 compared to the initial download time of 10, because 4 people can help me, and then I need to help the others. So once it's my turn, it's only the maximum cooperative cluster size is 5, and therefore it's limited to this red line. So the lower bound would be the blue and the maximum of the blue, and then the red one. If you look in a real environment, there's a little bit of math you have to do, then the curve looks a little bit different, but you see already with the lower bound, you can already have a good understanding how much download time you could save. And this is quite good if you have a large number of devices around you. Now the question is how much energy I will get there. Here we gain the downloading time. And the question is how much energy I would need to use. So if I stand alone, then I could say I'm a 3G device. I could even say, let me go and take a new air interface that might be with higher data rate, will even ask for more energy. Or I'm sticking to that what I have, even the newer one, it doesn't matter, but I take only a portion of that content, and then I take the rest by incorporating entities. Important to note, even if you take more entities into consideration, it doesn't matter if you have 2 or 4 or 3 devices, the energy level is then the same, because it doesn't matter if you get 50% from a device 2 or if you get 33% of device 2 and 33% of device 3. So from the energy perspective of your own, it doesn't matter how many are helping you. Otherwise, it has a difference for the helping devices. Now, the other thing, how to make the exchange inside such a thing very effective. If you remember the coupon collector problem, there's network coding. Network coding can be done in the application layer, in the network layer, and even lower. But I just name it here, but I will not go into it, as we have one full lecture tailoring for wireless cooperation, as well as one full lecture on network coding, if you're interested. So the next thing I would like to look at is the medium access, what we can do there with cooperation. We have 2 examples for that, but this in the next part.